Video, we're going to look at writing polynomial equations if we know their solutions, and we'll also look at a case of an application to a polynomial function. So to start off, before we get too far, tying this into what we've done so far, we have graphed polynomial functions of degree 3 and degree 4, and there are some connections that were to be made there. One of those was the solutions, and when we look at graphs, remember the solutions are wherever we have x-intercepts. So you look at this first case, and we see this graph here for degree 3, which looks like that capital N type of shape. And with this x-intercept right here, we know we have a solution. So what we saw after that was how to solve these equations and also how many solutions there should be. And so when we know a polynomial is degree 3, we also know that there are 3 total solutions. So when we look at this graph and we see it has one x-intercept, well, remember on the x-axis, that's where real numbers are located. And so when we have one x-intercept, what we know now is there's one real solution to this polynomial, and that's based on us having that one x-intercept. So then we can now know that we have 2 imaginary solutions, which is another a synonym to the word zeros. We know there has to be 2 of them to get to our total of 3 solutions. Okay, so that's what we're going to relate to in terms of a graph. How many real solutions are represented? How many imaginary solutions would there have to be as well, even if we don't know what they are just yet? Okay, so let's look at another case here. We have degree 4 polynomial, which typically would make some sort of W shape. In this case, it's been flipped over, so it's more like a capital M. So we have degree 4, which should have 4 total solutions, which are also zeros. So what we can do now is we can look at our graph and see how many x-intercepts it has. We see an x-intercept here and here. It looks like we have 2 more over here. So for us, that means 4 real solutions, and that's because we have 4 x-intercepts. And since all 4 of our solutions are represented on the x-axis, that means this particular function has 0 imaginary zeros, imaginary solutions. And there's our total of 4. And it really is as basic as that. So we can look at another case down here, and we see degree 5. Now, we've never graphed that, but we now know what that would imply. There are 5 total solutions. And so we can look at our graph here, and we see that it has 1, 2, and 3 x-intercepts. So those would all be real numbers on the x-axis. So we have 3 real zeros, which then would mean that we would have to have 2 imaginary zeros to get that total of 5. Okay, the last one does have a special case here. If you look at it, we see it's degree 4, which is 4 real solutions, or 4 total solutions. And so when we look at the graph, we see that there are 1, 2, and 3 x-intercepts. And so that would make us tempted to say that there are 3 real zeros and 1 imaginary zero to get that total of 4. Now, that's actually not true. It's actually impossible to have an odd number of imaginary zeros. They always occur in pairs. And so you always have an even amount of imaginary solutions, like you've seen in the other cases, 2 here, 0 here, and 2 here. And so what's going on in this 4th case is one of these x-intercepts is a turning point. And because of that, we call it a double root. So I'm going to get rid of these blanks here. Let's highlight this point we're talking about. It's this one right here, where we have a turning point on the x-axis. And that turning point represents what we call a double root, which simply means that this point would count twice. So if you can recall any times that we've solved equations to where we had the same answer listed twice, this is the scenario. It's because our turning point is a solution. So let's just keep note of that. And so for this polynomial function, we can now say, knowing that this middle x-intercept counts twice, we could either say that there are 4 real zeros, or if you're looking at the x-axis, technically there's only 3 different solutions. So we could actually put 2 different things here. Most typically, we would see the answer 3 because you only have 3 different x-intercept values. But in reality, when you solve, you actually find 4 solutions. It's just one of them's repeated. And that would mean that we actually have 0 imaginary solutions. Okay, so there's the big idea, reminding us of how many solutions a polynomial has based on its degree. And what we're seeing now, discussing now especially, is how these imaginary zeros come into play. And a big feature is you have to have an even amount of imaginary zeros. So what actually we're going to do today, you might enjoy, because it's just going to involve multiplying polynomials together. And so it's back to that stuff of FOIL, if you remember that acronym for first, outer, inner, last, multiplying 2 binomials together. So there are some steps listed here telling us how we're going to approach this. And what I've done is to the right here, you can see what the step means. And so we're going to see scenarios where we already know the solutions of the polynomial, and we're going to figure out what could the equation have said. So to get started, we write our zeros, our solutions, as x equals, because remember, our solutions are x values. And so let's say you knew you had solutions of 2 and -2 and 5i. Okay, so one of them's imaginary right now. Well, based on what we had just said, you can't just have one imaginary answer. So you'll see step 2 says if any given zero is complex. So complex, we haven't heard that in a while. Complex means imaginary. So if you have an imaginary solution, it could have 2 terms, a real part and an imaginary part. But what's important is if you have one imaginary solution, you have another one that's just like it, except instead of being positive, it's negative with the imaginary part. So you see that here in this outlined over here. We have the same 3 solutions we had before, but we also have to have this one, the -5i. It's a guarantee that it's also one of our solutions. Okay, so working backwards, we're undoing all of our solving that we did before. If these are our solutions, then we had equations equal to 0 to solve for them. That's how we would have approached this when we solved. So what we see here is we're going to move each of these. So in this case, we would have to subtract 2 on both sides, for example. And so then you see that it says x minus 2. And so that's going to happen in every scenario. We either subtract or add. And now that the equation's equal 0, what you can see is that whatever our equation said, those came from factors that we had. So x minus 2 is one of our factors. X plus 2 is another factor. And then we also have these factors with x and the 5i's. And all we do at this point is we multiply together. So these multiplied to x squared minus 4, and these multiplied to the x squared plus 25. And just kind of recall, when I multiply these together, I'll get I squared. Something we still need to remember is that I squared equals -1. And don't worry, we're going to go through this in our examples shortly, but something to highlight there. I squared is always equal to -1. And then once we multiply one more time, we're going to get a final polynomial. So that's the point that we're finished. Once you have multiplied everything together and it's all equal to 0, this is one polynomial that would have the solutions that we listed. It's not the only, but it is one case. Okay, so let's look at another scenario here and actually go through all the steps together. So we're going to write a polynomial of least degree. So there are a lot of polynomials that would have these solutions down here, but If we only have 3 solutions, we're going to be done if we have a polynomial that says x to the third, representing those 3. So we're going to write a polynomial that it would have these solutions. So we recognize first that the degree is 3, which would mean 3 total solutions. Okay, so let's look here. If these are my solutions, step 1 says write each of them as x equals. We can do that. We have x equals -2, x equals 3, and x equals 7. Okay. Step 2 says if any of them are complex, if any of them are imaginary, make sure you have both of them, the positive imaginary and the negative imaginary. And none of these are imaginary, so we don't have to worry about step 2. So then we move on to step 3. Solve each equation for 0. In other words, make each of these equal 0. Well, very easy step. To cancel this -2, we would add 2 on both sides, and we'll get x plus 2 equals 0. And on the other side, the next equation, that is, we subtract 3 and subtract 3. So then we get x minus 3 equals 0 because those 3's canceled. And then the last scenario, we subtract 7, and we get x minus 7. Oops, don't need those yet. X minus 7 equals 0. Okay, because those 7's canceled. So we just completed step 3. All of our equations now equal 0. So what do we need to do? We need to write these binomials, these expressions as factors. That would mean to multiply them together. So we're going to take our x plus 2 and put it into parentheses here. We're going to take our x minus 3 and put it in parentheses and the x minus 7. Okay, so we have these 3 factors written in parentheses. If we can just find a way to multiply them together, then we'll be finished. So how do we do that? How do you multiply 3 sets of parentheses together at the same time? The answer is you don't. You just pick 2 of them. So keep it easy. In this case, just pick the first 2. There's no wrong answer here. But if we multiply these first 2 parentheses together, let's remind ourselves of how that works. Remember, for this, you need to multiply each term in the first factor times each term in the second. So the approach, a very systematic, would be take x times x, and you would get x squared. Take x times minus 3, and you get minus 3x. And then very similarly here, we need to take this 2 times x to get positive 2x. And 2 times negative 3, that would be negative 6. Okay. And so we've multiplied these, and we have not used the x minus 7 yet. We'll keep that. Okay, so I hope that looked familiar. That's something we've done several times, and if you enjoy that, then that's actually the bulk of this discussion today. So you might actually enjoy doing a lot of this, but we are not finished yet because we still need to finish multiplying down here. Now, before you do that, it's always a good idea to simplify. So the negative 3x and the plus 2x, they can be combined, right? And so we're going to get, in this first set of parentheses, x squared. Combine those, negative 3x plus 2x, that's minus 1x, or just minus x. And then we still have our minus 6 at the end. We still haven't used our x minus 7, but we are about to. So after this step, we should be finished with our parentheses, meaning that we'll be able to write our polynomial. So to multiply here, I am running out of room, so I already know I'm going to bring my work over here. But it's just like we did before. each term in our first factor, each term in our first set of parentheses needs to multiply with each term in the second set of parentheses. So let's talk about how that's going to work here. We take this x squared, for example, and we're going to go multiply it to this x. So x squared times x is x to the third. And then we'll take x squared times -7. That's -7x squared. And keep track of these exponents. It's going to be important when we combine like terms. Okay, and let's go to the next term here, the -1x. We need to take that times x. So -1x times an x, that's -1x squared. And -1x times -7, that's a negative times a negative, so we get plus 7x. And then lastly, we need to take our multiplier -6 times these factors, times this factor x minus 7. So -6 times x would be -6x. And then -6 times -7 was going to be a negative times negative, so we get positive 42. Okay, put an equals 0 on the end of that. And we technically have a polynomial expression, but it's not simplified. So let's combine our like terms. We have an x to the third, and it's the only one. So we get x to the third. And then we can combine the x squareds. So -7x squared minus 1x squared, that's -8x squared. We can combine these like terms, 7x minus 6x, that's plus 1x or just plus x. And then we have a plus 42 at the end that we can't do anything with. And that's all equal to 0. And that would be a polynomial that would have our solutions that we started with of -2 and 3 and 7. Okay, so it seems sort of simplistic. Yeah, we have to go through some work to multiply everything, but overall, not the most complex thing that we've done. But speaking of complex, we can have imaginary solutions too. So let's look at a couple examples there. So in these two examples, we're going to do the same thing, just with some different things that could happen. For example, in number 2 here, we're going to see 0 as a solution, which isn't any more complicated, but it looks a little different when we start. And imaginary answers are going to start showing up. So in example 2 here, we have 4i. All right, so I'm not going to fill in the degree blank just yet. Let's talk about what this polynomial needs to say. So if I have solutions of 0, 2, and 4i, I understand that those are x values. And so we start with x equals 0, and then x equals 2, and x equals 4i. Okay. And so I'm going to say that's step 1. Write out your solutions as x equals. Now, step 2, if you remember, says if you have any complex solutions or imaginary, you need both that solution and its conjugate present. And so that's what's missing here. You see that we have x equals positive 4i, but we don't have the negative of that solution. And so that's our job in step 2 here. We're going to write all these solutions out, but we are going to make sure we include both positive 4i as well as negative 4i. So now that we've checked for our imaginary solutions, I'm going to fill in this blank up here. We know that the degree has to be 4. And so our polynomial in the end has to say x to the 4th. Okay, so step 3 says write each of your equations, solve each of them for 0. So make sure each of your equations, and remember, equations are just expressions that involve an equal sign. So we actually have 4 equations right here. X equals, x equals, x equals, x equals. We just need to make sure all these say 0. Now, here's why this one's kind of weird. Your first one already equals 0, so you don't need to do anything to this one. And sometimes we don't like that. But the next 3 we can. We see that you can subtract 2 here to cancel those 2's. right? So we get x minus 2 equals 0. And then the other two cases, same idea. This to cancel over here, we need to subtract 4i. So we'll also subtract 4i on that side. And to cancel here, to cancel this negative 4i, we need to add 4i to cancel. And so we'll add 4i on this side as well. And what's that give us? So here we give x minus 4i equals 0. And x plus 4i equals 0. Okay. So there's our four equations. They all equal 0. Okay. Step 4 says write these expressions on the left side of these equations as your factors. And so what we need to do is we need to take anything that's on the left side of the equal sign. Doesn't matter how many terms it has. So in this case, we just have an x, which is fine. In this case, we have an x minus 2 and an x minus 4i and an x plus 4i. Okay, so whether there's one term, two terms, three terms, we'll take whatever's over here, put it inside parentheses as our factors. So this polynomial would have factors of x and another factor of x minus 2 and a third factor of x minus 4i and a fourth factor of x plus 4i. And so we're going to be finished now as soon as we have multiplied all of these factors together. So a little strategy here. When you choose to multiply and you have a lot of parentheses to work with, main suggestion is anytime you have these things called conjugates, which are expressions that match each other, except one has minus, one has plus. Anytime you have conjugates, make sure you multiply those together because those will force terms to cancel. Meaning that over here, we'll multiply these together. So for step 5, we can go ahead and, I think that's step 5. Step 5 says multiply the factors together. So let's do that. Multiplying these together, we can take any two at a time. So if we want to multiply the first two together, that's fine. If you also want to multiply the last two together, also fine. So let's look at this first scenario. Not so bad. We're just taking x times whatever's in the second set of parentheses. So x times x is going to be x squared. And then x times negative 2 is negative 2x. Okay, and these next two factors, we will multiply the x and the minus 4 times the x and the plus 4. So we'll take x times the x, which is x squared, x times a positive 4i, that's plus 4ix here, and then negative 4i times x would give us minus 4ix. Not sure the order really matters there. And then lastly, we take a negative 4i times a positive 4i, negative 4 times positive 4, that's a negative 16. But don't forget that I times I equals I squared, which is actually going to be a big deal for us. So we have our two factors, and before we multiply them together, we really want to simplify. So this first scenario is fine. We just have x squared minus 2x. Nothing to do there. But in the second set, you can see a couple things. We have an x squared. And then the positive 4ix and the negative 4ix actually cancel each other out. And so what do we have left? We have minus 16i squared. But remember what we had said before, reminded ourselves before on the front of this set of notes, is that I squared is always equal to a negative 1. And that's helpful for us because when we write polynomial expressions, they don't include the letter I in them. And so here, when we have minus 16i squared, it's helpful that we know that we can rewrite I squared as negative 1. Okay, and so if we did that, what would our polynomials say, that factor anyway, we would have x squared minus 2x here. But in that second scenario, we actually end up with x squared plus 16. And notice there are no i's anymore. So by using our properties, we now have two factors that do not include the letter I, meaning we are ready to go ahead and multiply together. We'll take x squared times x squared, that is x to the fourth. X squared times 16 is plus 16x squared. Negative 2x times x squared is negative 2x to the third. And negative 2x times 16 is negative 32x. Which is great. This is actually perfect. The only thing that we could do better is put our terms in order. Notice the x squared and the x to the third are out of descending order. And so that's the last thing I'll do here is write it as x to the fourth minus 2x to the third plus 16x squared minus 32x. And so what we see now is our polynomial that has x to the fourth. So it's degree 4, which means that has 4 solutions, just like we started with. And it's just one scenario that would have these 4 solutions out of many. And that one is good enough. Okay, so let's try this one more time. In this case, you see there is a imaginary solution, a complex solution, but it has 2 terms involved. So let's just show what that would look like here. All right. So for this third scenario, we have solutions of, we can number our steps again, solutions of x equals negative 5 and x equals 1 minus 2i. And step 2 would tell us that if you have any complex solutions, so not this negative 5, but the second scenario where we have 1 minus 2i, if you have a complex solution, you need its conjugate as well, which just changes that minus sign to a plus sign. So we have 1 minus 2i and 1 plus 2i as our 2 complex solutions, which means that we have 3 solutions in total, which is degree 3. And we know our polynomial needs to say x to the third. And it's very, very important that you have these conjugates, because during our multiplication, that's what causes terms with the letter I to cancel away. So we get our polynomial that's all in terms of x. Okay, so step 3 says write each of these equations as equals 0. And it takes just slightly more work on this one, not much. First scenario, we're fine. We add 5 to cancel. And we get x plus 5 equals 0. And when we get comfortable, we tend to make a little mistake on these next two. But if you go slow enough, you'll be fine. This is a positive 1. So I think we understand to cancel a positive 1, we need to subtract. And this is a negative 2i. So to cancel that, we need to add. Okay. And so that's also going to happen over here. But the idea is let's cancel on this side. Let's use opposite signs. And now we've done that, look at what the left side has to say. It has to be x minus 1 and x plus 2i equals 0. And this last equation, that's a positive 1, so we subtract to cancel that. This is a positive 2i, so we subtract to cancel that. Okay. Cancel and cancel. And if we subtract those on the right side, we subtract those on the left side, which gives us x minus 1 minus 2i equals 0. All right, so we have all of our equations set up, meaning we now know what our factors had said. The first one was x plus 5. A second factor would be x minus 1 plus 2i. And a third factor would have been x minus 1 minus 2i. And we know the equation was equal to 0 because that's what we set our factors equal to. All right, so let's see. Now that we have our factors, we need to start multiplying. And again, there is some strategy here. As you start multiplying, pick the conjugate factors first. So definitely multiply these together before you start. Okay, so we're going to leave the x plus 5 as it is. We'll come back to it. The second set we have to be detailed here because if you recall, there are 3 terms in this first factor, and there are 3 terms in the second factor. And so that means when you multiply these 2 factors together, 3 times 3 is a total of 9. So we're going to get 9 different terms from this multiplication. And we want to make sure we get all of the signs right and include everything we need so that we don't have to back up and fix anything. So be careful here. Let's get started. You're going to take x times all 3 of these. So we'll take x times x. That gives us x squared. X times negative 1, negative 1x. And then x times this negative 2i, which is minus 2ix. Let's do the same thing with our negative 1 in this set of parentheses. So negative 1 times x is negative 1x. Negative 1 times negative 1 is positive 1. And negative 1 times negative 2i is positive 2i. And then lastly, 2i times x is plus 2ix. 2i times negative 1 is minus 2i. And then 2i times negative 2i is negative 4i squared. And there's that I squared again, which we know is going to be rewritten as negative 1. Okay, so we still have some work to do. Let's see what we have, though. Before you try to multiply x plus 5 with this second set of parentheses, most definitely simplify that. So this is the only x squared term, so we're okay to write that down. Now let's see what else has happened. We have a negative 1x. Let me try to keep track of these. We have a negative 1x here and a negative 1x here, and that looks like all of our x's, so we get minus 2x from this. Yeah, we'll put that in green. Okay. Now let's see what else we have. Remember, our polynomials are not supposed to include the letter I when we write those polynomial equations. So let's see what happens next. Hopefully something good. We have negative 2ix. We also have, if you look, a positive 2ix way over here. And since those are opposite terms, those cancel each other out. So we don't have to worry about those anymore. Okay, so let's go another step. We have a positive 1 here, and we don't see anything else that has a 1. That's just a number, so we can put that plus 1. And then another good thing's about to happen. We have a positive 2i and a negative 2i. So those cancel, which is nice. We don't want to have the letter I anymore. And then in that very last scenario, we have minus 4i squared. And so it's the only term we have left, so I can put that down. There's nothing to cancel with it, except we remember that I squared equals negative 1, so we put a negative 1 for that I squared. And something nice happens there, and all of this is equal to 0. What happens in this second set of parentheses is we have a little more simplifying. So we have x plus 5, and then we have x squared here, minus 2x plus 1, but negative 4 times negative 1 is plus 4 equals 0. Okay, so we get x plus 5 times here. Simplifying one more time, we get x squared minus 2x plus 5. And just like that, we have factors that do not include the letter I whatsoever, meaning our polynomial will only involve terms with the letter x. So let's finish our multiplication, just kind of reminding you here, when we multiply x plus 5 times these three terms, when you take 2 terms times 3 terms, you're going to get 6 terms altogether. So let's be detailed. So we take x times x to the second. That gives us x to the third. X times negative 2x. That's negative 2x squared. X times 5 is 5x. 5 times x, and now we need to take 5 times this set of parentheses. So 5 times x squared. 5 times negative 2x. And 5 times 5. And there are the 6 terms that I was referring to. Okay, and if we can just combine like terms, we should be finished here. So we get x to the third. And then we have the negative 2x squared and the positive 5x squared. That is plus 3x squared. We have 5x minus 10x. That's minus 5x. And then we have a plus 25 at the end. And all of that's equal to 0. And now we have our polynomial equation. And so x to the third plus 3x squared minus 5x plus 25 is a polynomial function that has negative 5 as a solution, as well as 1 minus 2i and 1 plus 2i. And that pretty much covers everything we need to know about working with solutions and getting back to the polynomials that would contain those solutions. There are some other things we could look at. Some of these rules, the rule that we have for imaginary solutions, for example, also applies to radical solutions, things that involve square roots, for example. They have the same rule where you have to have 2 of them. But we'll leave that for another time and just work with our imaginary solutions today. Okay, so one last thing I thought that we could do that is somewhat interesting is an application, but actually all of the work's going to be done with a graphing calculator here. So what we're doing in this scenario, this very last case, is looking at a situation where we're going to create a box. Now, the thing is, we have some option into how big of a box it is. How this works is you have a big flat sheet, a cardboard sheet that is 16 inches long by 10 inches wide. Okay, so you just have this rectangle. So these dashed lines inside, those are just cutting lines. So we haven't actually cut into the box yet, but we will. So the way that we're going to create this box is, I need to change this, 16 inches and 10 inches, is we're going to cut corners out of equal size. So we don't know how big of a corner. That's why we see the letter X here. But if you can visualize this, there are some folding lines in this picture to where after we cut out this square, we're going to have a flap right here that we would fold this upward. So you can try to picture folding a box upward here. When you fold this flap up, it's going to be X units tall. And that's going to happen everywhere, because if you cut out this corner, you're going to have another flap on this side that folds up, right? And the same goes for all of your sides. We'll have a flap here that will fold up and a flap over here. And so the overall idea is that we're going to fold all of these flaps up, okay, to make a box. So all of these flaps are going to meet up. Now, there won't be any top on this box. It's going to be an open top box. All right. So what are we doing here? We're going to look at how we can express the dimensions of this box using the height, length, and the width. So let's look at that just a little bit. The height, when we fold up these flaps, we know is going to be X. Okay. because when we fold these flaps, that's how tall each flap is going to be. And we don't know how much X is. Maybe it's 2 inches, maybe it's 6 inches. We actually get to choose that. We have some choice there. Okay, so the height is X. What does that mean about our length? Well, the length was originally 16 inches all the way across, right? But if you cut out X amount over here and X amount over here, what are you left with? Well, it turns out you're left with a length of 16 minus each of these X's. And so for us, that means that this space is 16 minus 2x. And very similarly, the width is no longer 10 because we're taking x away here and x away here. And so for us, that's going to give us 10 minus 2x. Okay, so this space is 10 minus 2x. And again, everything is based on x. If we decided to cut out corners that are 7 inches, then now we know how long our length and width are. Okay. So writing a polynomial, what we're going to do is we're going to write a polynomial function to represent the volume. And we're actually just going to write it in factored form. So if you remember volume, that is calculated by length times width times height. And so what we can do now is we can take our three expressions up here for the length, the width, and the height, and just show that we're going to multiply them together. So we get x times 16 minus 2x times 10 minus 2x. And rather than working this one by hand, that would take us a little bit of time. We're just going to go into a graphing calculator such as Desmos to see what this graph would look like. So I'm going to type in this equation, except instead of v of x, we're just going to put it as y equals. So y equals x times 16 minus 2x times 10 minus 2x. Okay, and so going here, I actually think I misspoke. I think we can actually type this in function notation where we put v of x equals and put x times 16 minus 2x times 10 minus 2x. And Desmos is creating the graph representing our volume. So we've written this as v of x, meaning our volume equals this. And we can have a lot of volumes depending on what size of corner that we cut out. So I'm zooming out a little bit here so I can get a better look at the graph. I know it's supposed to kind of look like the letter N, and I see that it turns. It has its turning points in this area, but I have a lot of wasted space, so I can't really see the graph that well. So I am going to change the settings here to not look out so far on the x-axis. So on the x-axis, I'm going to change this on the left side to just go out to -10. And on the right side, I'll try the same. Just have it go out to 10. And there we go. So here's our graph. So what this graph is representing is our volume of the box, because that's how we set up our equation. So I could look at anywhere on this box, and if I click around and drag, that second number would be the volume of the box. The first number would be how big of a corner we cut out. So if we had a corner of 0.84 inches, a height of 0.84 inches, we'd see that the box would end up being about 100 cubic inches in volume. So let's go back to our scenario and see what we were being asked. We were asked, what is the x value of the box with the maximum volume? Well, if this graph is representing our volume, where would a maximum occur? And if you remember, we talked about maximum and minimum values, and those happened at turning points. And so when we look at this graph, we see that it turns right here at 144. And we could look and ask if there's any other maximum values. Well, you could say, yes, the graph keeps going up, but then you'd have the graph going up forever. And is it likely that we're going to have a box with a volume of infinity? And the answer is no. So we're going to stick right here for some reasons that we'll talk about in just a moment. But if we look at this maximum point, this turning point that's at the top, we have 2, 144. So the x value here is 2. The y value is 144. And so the x value of the box with maximum volume is 2. And the maximum volume that went with that, which was the y value, was 144. Which is in inches, and that is cubic inches. That's the unit of measure for volume. Okay. So now that we have that, just by looking at a graph, we can answer this next question that's asking, okay, so you know that the biggest volume is 144 cubic inches, and that happens when your x value is 2, then how big is your box? How big is the height, the length, and the width? Well, we can do that now because we define them up here. We said our height is just x. And so if our maximum volume is happening at an x value of 2, then our height is just 2. And for the same reason, our length is 16 minus 2x. And so our length is 16 minus 2 times 2, which would be 16 minus 4, or better yet, 12. And then our width, same deal. We have 10 minus 2x. So our width is going to be 10 minus 2 times 2, our x value, which is 10 minus 4, or 6 inches. And you can see there, we're saying that our box has dimensions of 2, 12, and 6. And if you just check your volume really quickly, our volume would be what you get when you multiply those together. And when you take 2 times 12 times 6, it just so happens that you end up getting 144, just like we said. Okay, so are there any limitations? Can we pick any x value ever? Well, no. Remember, this box is only 16 inches by 10 inches, so you can't cut out more of the box than you have. So there has to be a limit to how big of a corner we can cut out before we cut out too much. And so that's the last thing we're going to look at here. If we go back to our graph and we look at where the graph is above the x-axis, well, because our graph is representing our volume, anywhere we're above the x-axis, that's where our volume is positive, which makes sense. Those are numbers that make sense, having positive volumes. Well, what heights are possible for a cardboard box? Well, our height, remember, was the letter x. So when we talk about what heights, we're talking about what x values are possible for the cardboard box here. And if you come up here, when would our volume be positive? What x values would we have to be between? Well, we can see it right here. We have an x-intercept on each side of this part of the graph that's above the x-axis, meaning the x values you can choose from are anywhere from 0 to 5. So we can cut out corners that are more than 0 inches, but you can't cut out corners that are 5 inches. Because as soon as you do that, you get a volume of 0. Cutting out a corner of 5 inches won't let you make a box, in other words. Same thing here. You can't cut out a corner of 0 inches because then you don't have any flaps to fold up. So we have options for how big of corners we cut out, and those options are limited to any values between 0 and 5, as demonstrated by our x-intercepts. So let's go back here. And we know that they have to be between 0 and 5. And those are coming from x-intercept values. And what we would see is that if we used other x values, two things, the volume would either be 0 or a negative value. Which wouldn't make sense. And so that's why our options would only be from 0 to 5. So approach this the same way in your assignment. That we'll just practice this little application there, and that will conclude our little lesson of writing equations given our zeros.